I'd like to first thank the organizers for letting me speak here. I am a bit of an outsider to this community, although I do talk to climate scientists. I'm an applied mathematician, and as such, I might be open to criticism of being a bit out of touch with reality and maybe being too aloof, but I can take that and I can reflect it back in a number of cases. So let's see how it goes. I'm not particularly used to standing and speaking from a podium and using a remote that I'm not used to, so might be a challenging task. By the way, I have time until 5:02, right? Is that? Okay, great. So I hope the title summarizes what I'm going to talk about. It is a bit long, but I wanted to focus on trying to squeeze the issue of probabilistic predictions using reduced order models into an information-theoretic framework. In particular, I will want to say a few words about multi-model ensembles. That's going to be the main theme, although I will use some other examples and topics as well. So as a motivational slide, I've got a few sketches, and I have quite a few sketches. I added also some more pictures in order to make it lighter. So what are the main building blocks of what I'm going to talk about? Well, I want to concentrate on improving probabilistic predictions of complex systems. So what I'll be dealing with, is either stochastic models with, for you, they might include stochastic parameterizations, or deterministic models, which include various realizations starting from different initial conditions. At this level, I will not care about what kind of models I'm dealing with. All that is important for me is that I can represent the dynamics of my models by an evolving probability density function. And the rest of the details I will sweep under the carpet. I know they might be important for various applications, but they are not particularly important for what I'm going to talk about. And we can argue about the details later. So this issue of optimization of reduced order moments for best predictions, in my mind, it can be split into at least two different parts. So one I'll call the tuning. Let me just find the laser here. Okay. And the tuning is going to, again, I'll divide my problem into two different segments on the time interval. I'll deal with something called the training phase and the forecast phase. And in one case, I'll be interested in trying to tune my imperfect models, my reduced order models, on the attractor of the true dynamics using historical data, so that I can do predictions accurately. And I'll say what I mean by accurately in a second. So there's two different scenarios here. What I'm sketching here are two different probability measures, mu and nu here. I can't draw a probability measure. I'm just drawing, say, the mean of those two measures. So I would like to get some agreement in the training phase, so that when I start running the models forward, I stay close to the true solution in a sense that I'll describe in a second. Of course, what normally happens if I do it incorrectly in sufficiently complicated systems, by most nonlinear chaotic systems and stochastic systems, I will schematically very quickly diverge from the true solution. The other part is, of course, what one might do after we start forecasting, and I would argue that the way of keeping the predictions close to the truth would involve data assimilation or stochastic filtering. I decided to skip stochastic filtering from this talk because it would be too many details, so I'll focus just on the first part. So I keep talking about those probability measures or probability densities, as I will quickly turn into. Well, I already indicate, well, I have to have a way of measuring what it is. I mean, how do I decide whether or not two probability measures are close to each other? So we'll get to this quickly, and it will be an important part of the talk. But let me first, again, motivate it by another sketch. So suppose that we have a bunch, oops, that's already my problem with the remote. Suppose we have a bunch of models available, all of them imperfect. Okay, so in this sketch, the red one corresponds, again, I'm shading the probability density associated with the truth, which I don't know in principle, and there's a bunch of models, and they evolve in time. And these are all sketches of the probability densities. And let's imagine that, for example, at this particular time, well, I want to have either a single model or a bunch of them and combine them in such a way that I will be able to approximate the truth in as good a way as possible. Well, the question now is, well, in order to do this, should I use a single model or maybe an appropriate mixture of these models? In other jargon is the ensemble of models. Well, in particular, you can see, just again, for the yellow one at this particular time seems to overlap the most with the true probability density. And the question one might legitimately ask, well, is it better to use this particular yellowish guy at this time, or maybe I should use a combination of models which, on the face of it, on this sketch, appear they are spread around the truth? Would I be better off using a mixture of those guys, or the one that's really overlapping the most with the truth at this time? And that's, I'll argue that, well, first of all, it depends, but the answer is not. It's not always that obvious. And the first time I started thinking about this, I attended a meeting, I think it was at Scripps, a good couple of years ago, which was devoted to multimodal ensemble predictions. And the standard approach was, for various political reasons as well, to just, well, if we have a bunch of models produced by different labs, well, let's just use all of them and weigh them equally. Okay, and that's probably going to give a better result than using a single model. That's not the case, and it's known in the community as well. But I want to go more into the geometry of the problem and sort of shed some more light onto this issue. So what I'll be after is, I want to derive some information-based condition which will guarantee the utility of a multimodal ensemble. So, i.e., when is it better to use a multimodal ensemble versus a single model, which might in some way be the best, okay, depending on which metric I use. Well, just as a motivation here, well, this picture appeared before here, so well, there's a standard prediction of the global mean temperature. There was a sort of training phase when people have enough historical data, and of course, once you start using various models into the future, you get a big spread. The question is, how do we decide which prediction, or how should I combine these guys in order to get something decent? And that's another one where I'm using isobars here from a different, but this is just a motivation here. So again, still in terms of sort of outline and summary, what I already hinted at, I will have to use a particular metric, if you like. I put it in quotation marks because it's not going to be strictly a mathematical metric. I have to be able to assign some notion of distance between probability densities or probability measures. So the reason for this, and again, I sort of the sketch first. Well, I have to be able to say, if I have these two different probability densities in this case, the red and the green one, and these two different cases, well, which one is farther? Or which are these two densities farther from each other, or maybe this this red one is farther from the green one? And then, of course, well, I'll get into the sort of necessary condition for using mixture models instead of single model in terms of this particular metric. I'll relax it a little bit into something that's perhaps more manageable in terms of applications, although probably most of you will tell me that it's still not particularly manageable. We can talk about it later. So the metric, I'll talk about it in more, I'll give a few more details in a second, but this metric that I want to use, I wanted to satisfy a number of properties. One of the important ones is the convexity in the second argument. I'll describe the details in a second. This particular feature is satisfied by many metrics in general, but what I want in addition to this is a following triangle-like equality, okay, which most metrics do not satisfy. And for this reason, I will mostly focus on something called the KL divergence, which actually happens conveniently to satisfy these properties, and it helps me a lot. Then I'll describe the particular condition which will guarantee me the utility of will tell me when I should use a multimodal ensemble versus a single model. And I'll relax this condition in subsequent discussion. Just a few words, again, because I probably will not have time to go to the later issues, but I wanted sort of to advertise it before I go on. So the KL entropy, KL divergence that I'm going to use, I mean, it's a part of larger class of divergences, which are called, or one can call them bi-entropies. I'll be using this KL divergence, Kullback-Leibler divergence, which is defined here as the expectation on, okay, I mean, it's maybe a bit too abstract, but I mean, I'll rewrite it in a second. So this is the expectation of a particular random-Nikodym derivative of the two measures. Bottom line, it will allow me to say whether or not two probability measures are far from each other or not. How much information is lost in one probability measure relative to the other probability measure. In particular, the other will be my reference true measure. This is nice from the mathematical point of view, as it turns out, because then I can, within this framework, I can come up with number of bounds and inequalities, which again, for example, can give me certain bounds on the performance. If I try to compute prediction of a particular observable, say the mean temperature, and I have now I'm looking at the expectation with respect to my true measure and the approximate measure, I can come up with bounds which, well, instead of in the product form, this term here will only depend on this metric on the probability measures. So in a way, if I'm able to reduce the lack of information between the measures, I can bound the error in the observables automatically. Yes?
These are measuring model diversity. There's no, truth hasn't, the outcome hasn't.
Not at this stage yet, no. So this is at the moment. I just wanted to sketch the general framework. At the moment, I have no truth and no approximation. I just have two different probability measures or probability densities. Okay, and in order to be able to compare them, I have to introduce an additional structure onto the manifold of these probability measures so that I can tell which one, how do they relate to each other. Okay, but then, as I say, this framework allows me to then push the issue much further. For example, in terms of coming up either with these bounds on the observations, and also carry out something called a sensitivity analysis, which again is in a way, well, sort of baby approach to climate change type scenarios. Okay, if I perturb my equilibrium probability density by a bit, can I say something about what's going to happen in the future on the perturbed attractor? Okay, so the outline of the rest of the talk is as follows. I'll give more details on these information-theoretic tools. In the meantime, I'll sort of try to argue why and when the multi-model ensemble predictions are useful. And rather than giving a sort of detailed mathematical exposition, I'll do some sketches, but that's not really related to this geometry word here. I do want to sort of put this issue of multimodal ensembles in the particular geometric context, okay, which will be facilitated by the particular properties of the divergences that I'm using. And hopefully it will shed some light on the issue when multimodal ensembles are useful and when they are not so useful. Okay, I know that most people know that in some cases, if you have a bunch of models, that it's not always the best idea to just run all of them and hope that and people know that sometimes it doesn't work. What I was interested in, well, can you say anything more about this? When does it not work? And what is the associated geometry of the problem which leads to it either working or not working? I hope to get to at least one of these examples here. We'll see how we go. This one is a bit more atmospherically motivated, so hopefully I'll have enough time. So a simplified definition of my KL divergence, which will be the main tool. So this is the way I measure discrepancy between the two probability densities. It's nice because it has a nice information-theoretic interpretation, because it really can be interpreted going all the way back to Shannon as the lack of information in one probability density relative to the other probability density. So in a way, I'll be monitoring how much information I lost by using an approximation. Okay? It's not a metric. It's not mathematically. It's not a metric. It retains some features of it. It's non-negative, and it's zero if and only if the two densities or measures are the same. But it's obviously not symmetric, as you can see from this property. However, now we're getting to the important thing. Now it satisfies this triangle-like equality, but only on a specific type of probability density. So these are these pi L's here. By pi L's, I denote the so-called least bias densities. I will not go into the detail of it. These are sort of In other world, these are called the maximum entropy densities. All this means here is that if I want to consider the lack of information in the density Q relative to P, I can, and if you tell me not the full, if you give me not the full information about P, but you tell me, if you give me some constraints, for example, you tell me what the mean is and what the second moment of the density is, I can construct the so-called least bias entropy, least bias density, or the maximum entropy, which will satisfy these constraints. And this is the pi L here. And it turns out that for this kind of densities, I can split this lack of information between P and Q into this sum here. And the first term, well, they're different in nature. The first term we call an information barrier. Why? Well, because it only involves the information about now P will stand for the truth. Okay, so it involves the lack of information in this approximate density given the fact that I measured maybe a few moments. And the truth. And the second part, well, it involves the stuff I have access to. So this maximum entropy given that you told me, well, the mean is this, and the covariance, for example, is this. And now I can deal with my models, with my reduced order models, and I can minimize the first part. Okay, the second part. The first part I can't do much with unless I have more measurements or access to better measurements of the truth. By this I mean, so if I can improve, if I have more constraints, I'll be able to construct a more accurate approximation of the truth and perhaps reduce this information barrier. But the main point is that I can, by playing with models in this information, I can try and reduce this model error, or this lack of information, and the problem splits nicely into two parts. Why do I care again about these issues? Well, it turns out that within this framework, and again the picture is repeated here, this is a schematic thing. Sorry, I still got a cold. What I can show is that, for example, well, if I'm able to tune my reduced model in the training phase, given that we was on the attractor, and then if I perturb the attractor, then I can obtain guarantees, which are again in the form of maybe not a particularly transparent inequality, but I'll explain what it means in a second. Then I can get a guarantee that if in the case of perturbing the attractor, I will, so just tuning the attractor in the training phase will give me some guarantees on the error I'll make later on, provided that I do this sort of what I call a forced response. I'm perturbing the attractor. On the other hand, if I look at the sort of general initial value problem, I start from an initial condition which is arbitrarily far away from the attractor, then tuning the attractor, unsurprisingly, if you did that with dynamical systems, tuning an approximate model on the attractor doesn't really help me much with saying anything about the dynamics away from the attractor. And in this case, the only hope I will have is sort of predicting it over a sufficiently short time interval. Well, this inequality here basically states what I just said here. So the error, the lack of information in the forecast phase, which is expressed by this term here, I can bound it by certain coefficients which are computed on the unperturbed attractor. This is a vector of expectations. I will not go into details to here, but what is important here is the order, is the O terms. Okay, so if I look at the issue of forced response, so if I perturb the attractor, assuming the attractor of the perturbed system exists, using the so-called linear response theory, I will get guarantees that this term is actually small. So this bound makes sense. On the other hand, if I'm looking at initial value problems, this term does not necessarily have to be small. So in a way, this bound is not of particular use. However, for forced response, I find it quite nice because these coefficients are effectively Lagrange multipliers that I can compute in the training phase. So I don't need to forecast in order to have some bound on what is going to happen in the future. Similar thing, I'm sorry, I'm recovering from a cold. Similar thing can be done in the multi-model case, except that now the main thing is to look at here. Well, you can see that now I have much more freedom in minimizing this error because now I have a whole mixture of these parameters. I have many more degrees of freedom that would allow me to reduce the error in the predictions. Okay, so there's an added a benefit in principle of using multimodal ensembles, because I mean these are just my weights in the mixture density, and by choosing appropriately the weights, well, I can make this factor here maybe not necessarily 0, but I have more ways of minimizing it than in the context of a single model. Having said that, well, as I already hinted at, and that's well known, and multimodal predictions are not always the best. And I'm just showing you a sketch. I will not say this is related to one of the examples I have at the end. I might get into this. But for now, what is just important is the sort of schematic illustration of this. So what I call a prediction error here is, again, the lack of information between the prediction of my reduced model versus the truth. I'm playing God here, and I know what the truth was. And this is time here. And what I'm showing is 2 different cases where I compare the prediction using a single model, which is best in a particular sense, in the sense that, that the correlation time of the dynamics is the same for both the truth and the approximation. And the blue and magenta lines correspond to this error for equal weight ensembles, which is the blue guy here, and magenta is a multimodal ensemble with optimal weights. As you can see, and these are sort of the distribution of the weights here relative to the single model here. And what you can see here is as well, in some cases, just if we look at it, well, using equal weight ensemble does quite a bit better than using a single model, which is in a sense optimally tuned to the true dynamics. But in other cases, and I might get into this, the equal weight ensemble actually does a pretty poor job. Perhaps not surprising, but maybe worth mentioning. Also, another issue is that if you look at the distribution of the weights in the ensemble, in my multimodal ensemble, again, depending on the dynamics, my weights, the optimal weights will, in these cases, they lie on 2 different sides of this. So it's indexed by the correlation time. Here, my models all have a larger correlation time than the green guy. Here, they have a smaller correlation time than the green guy. That's just an illustration. So let me say something a bit more about, and go back to the original question of when is the use of multiple models better than the use of a single model. And it can be encapsulated in the form of a theorem. I'm not going to go to this. The details are in this paper here. Just wanted to flash the fact that it exists, and I'll go into pictures. So let's first look at just these sketches. So what I said at the very beginning, the measure I use for determining the lack of information between my approximation and the truth is given by this KL divergence, and the KL divergence, as in other metric, is convex. In this case, it's convex in the second argument. Okay, so this is my convex landscape. It's a sketch. It's a one-dimensional sketch here. So the answer to the question, sort of the quiz I posted at the beginning, let's imagine, so now this is the best I can do, given by this black dot. And this would be my best single model, the red guy, because on the vertical, so the vertical would be my lack of information. So now, if you look at this plot here, of course, if I have this single guy here, well, can I do better than just using the single model here? Well, in the sketch, if I use the the average of this green and the blue dot here, I'm going to end up, due to the convexity of this metric, in something that in general has a much lower lack of information than the single best model. I'm not particularly good at drawing infinite dimensional pictures, which it should be, but this is a sort of equivalent in 2 dimensions. So the red corresponds to the isocontour of this red dot here. Well, you can see that in particular, if I happen to have something, if you like, on the other side of this convex landscape, then I can do better by combining my imperfect models relative to using my single model, which has the best property in terms of minimizing the model error individually. Of course, there's another situation. Well, there's more cases here. I mean, I can have anything on the other side of this convex landscape, even if this model has a much larger lack of information. I can still, by taking the even equal weight ensemble of those, I could reduce my model error. However, the problem is, of course, that I don't in general know whether or not these models, which side of this convex landscape these models lie on. Okay, and this will be the reason why, well, I'll come to a simplified criterion. So the general criterion here, which is easy to state, is more difficult to evaluate. Well, I will say that the multimodal ensemble, for example, will be performed better than this red guy here if the lack of information in the multimodal ensemble relative to the truth is smaller than that for the single model. That's easier said than done. Again, because of the, I can sketch this, but I can't quite evaluate this. So what in the situation, so that's kind of driven by the more practical approach. Let's say now that all I have is I can evaluate the lack of information in each individual model in my multimodal ensemble relative to my least biased approximation, this pi r. So this corresponds effectively to knowing what the values on the vertical line are. But I don't know where these, what the projection was. I just know that these purple and the blue guys have the same lack of information. I don't know where they lie. Okay, so in principle, if I can combine a guy that lies on the other side of this convex landscape, I can reduce my overall model error. However, in situations where all my models lie on one side of the convex landscape, well, then I can't clearly, by taking any convex combination of the densities, I cannot do better than using the single best model. So the issue of this information barrier that I was talking about, again, geometrically corresponds to the situation where all of my models lie on one side of this landscape. Okay, so they're all biased in a similar way, if you like. On the other hand, if they are spread nicely around the minimum, then combining these models will allow me in reducing the overall lack of information. Well, there is an issue here, again, which is the fact that I don't know how to project these dots on the convex landscape. And this is, again, the few discussions I had with climate or with modelers is that, well, in principle, it is possible to use the first criterion, whoops, here, but this would require running GCMs for various weights and evaluating, running them each time you change the weights and trying to optimize for the weights. That is deemed infeasible in general. Well, people say, well, we can do it for once. We can evaluate what is the lack of information for a particular model relative to this least bias approximations, but don't ask me to change the weight and now put everything again back into the KL divergence and try to minimize this particular function because it's just computation expensive. Well, so what I have here is just this lack of information for individual models. And one criterion again here would be, well, it's easy to state, well, the multimodal ensemble, again, I'm using convexity here, but I'm not going to details. Well, it will be better if the lack of information between the single model I'm looking at is greater than a convex combination of the KL divergences for each individual model. All of these guys retain the metric property and they always non-negative, so this is a convex combination. There's a simplification of this, or making it a bit more realistic. What I mean is as follows. If I allow a bit of a leeway here by adding a control parameter, which is this delta, which allows exactly, given the fact that I don't know on which side of this convex landscape I am, if I consider this situation here with the delta, I allow in principle to include models which overall have larger information loss relative to my best model, but it might happen, and that's something I cannot get away from. It might happen that it will lie on the right side of this convex landscape. If it does not, well, I will increase my loss of information by controllable parameter delta. So this is my sacrifice. But by doing this, I might capture the models which lie on the right side of of this landscape, and then I'm gaining quite a bit more. So then again, it's well, I might have time to go through the two examples. The second one will actually, it's a toy model. I like it quite a lot, so I'll try to get to this because it is related again to these multi-model ensemble predictions. But first, maybe this will interest you a bit. This is related to tuning the attractor and trying to predict, to tighten the quality of predictions for the forced response by appropriately tuning imperfect model on the attractor. So this is more sort of geophysically related to geophysics. This is just a turbulent dynamics of a passive tracer. It's given by this parabolic PDE here. And well, this is just a sketch. It's not really related to what I'm talking about. But now it turns out that one can, this is actually, by the way, joined with Andy Maida quite a few years back. Turns out that if one considers this dynamics, one can find exactly solvable solutions to this generally complex PDE if we consider it in a narrow latitudinal strip on a sphere. And what we look at here is, well, we look at the dynamics of the tracer in the present of a that would be meridional gradient, sort of north-south gradient. So there's a gradient, and there's a perturbation here. It turns out that this dynamics has a lot of interesting features, which are again geophysically interesting. The first one is that it leads to non-Gaussian probability, time-dependent probability density functions with a lot of intermittency and sort of nicely turbulent spectrum. So my reduced order model again is going to, well, roughly speaking, is going to correspond to something that is resolved on a much coarser scale than the truth. Well, one often compensates for it by adding the so-called eddy diffusivity. What we'll do as well is add an ad hoc stochastic forcing. This can be justified. I'm not going to go into this. One would have to rewrite this equation in a spectral domain and do something with the nonlinear interactions. At the moment, this is just a sort of baby example when I have only one tunable parameter, the sigma t, which is the amplitude of my noise. This is the white space-time white noise, which I write in the physicist notation. Okay, so this w dot here. And I want to consider the first tune my imperfect model to the truth that I get from to my truth dynamics, which is resolved on a much finer scale, by pumping in stochastic noise into the problem at an appropriate level. And the appropriate level will be such that I will try to minimize the loss of information between the equilibrium density of my true dynamics and the equilibrium density of this approximate dynamics. So this is all going to be parameterized by this sigma t here. Okay, maybe I'll just skip to, I'll go back to this slide. So what happens, again, here is I'm minimizing the loss of information on the attractor, and what you can see here is that if I do not pump any stochastic noise in the problem, this is just, the scale on the axis is the same, and it's the loss of information. After pumping an optimal amount of noise, I can reduce the discrepancy between the two, between the model and the true dynamics in terms of the information loss by quite a bit. And what happens then now is I look at the forced response. I sit on the attractor of my true dynamics. Now I change the forcing. Okay, and what happens here? Now I'm looking at my forcing. This is the evolution in time. It's sort of just it's time dependent. Then it settles on a new. The perturbation becomes constant. What you can see here is, well, hopefully you can see it. The black, thick black curve. Sorry, the dashed dotted line is the solution of the unperturbed system. The black curve here corresponds to the solution of the exact solution of the perturbed system, and the red dotted line corresponds to what I can obtain from the linear response theory, given that I tuned my imperfect model appropriately on the attractor. Okay, so the first inequality I showed you was maybe to some extent vague. It just showed you that, well, there is a guarantee that for the forced response, if the attractor of the perturbed system exists, well, then we can bound it by trying to tune the statistics on the unperturbed attractor. This, if you like, is a baby evidence for this to be true. Okay, just let me just go back here for a second. I don't want to spend too much time on this, but it turns out what I said, that there is a lot of, one can come up with a whole class of exactly solvable or exact solution to this problem that I talked about. And it's also quite useful, I think, in order to test many hypotheses in geophysical context because of the richness of these solutions. First of all, it's an exact class of exact solutions to these turbulent tracer dynamics. Second of all, it has all these nice properties which are exhibited by both passive tracers in the atmosphere, as far as I know, and other quantities, which is this intermittency and non-Gaussianity. And also one can start looking at things, one can start analyzing the issues related to, well, what features exactly do lead to the onset of intermittency. And it turns out that, for example, in this model, the dynamics requires, I can talk about this offline, there's at least 3 separate dynamical ingredients which are necessary for these dynamics to be intermittent and non-Gaussian. And it's related to the nature of both this horizontal sort of jet and the velocity field which goes perpendicular. It depends on their statistical properties. So it's also a sort of nice toy model to try and identify what are the main ingredients which give you intermittency in observations of passive traces, for example. This is, by the way, I decided to keep this slide here. That doesn't, I wouldn't focus too much on this, but a while ago, I did start, well, we attempted to start a collaboration with people at PNNL in order to implement many of these ideas in a context of a GCM, mainly, in order to be more, for it to be more appealing to people who work on real problems. But this unfortunately stalled. Main issue was just sort of, we were talking a different language. So, but if there's anyone interested in this and capable of running big models, then let me know and we can talk about it in more detail. I'm open to further discussion. Okay, I've got still 5 minutes, so let me just go quickly through this last situation, last example, which I quite liked. It's very simple, but hopefully it will illustrate on a sort of specific case what I was talking about. And it's again illustrated to this multi-model ensemble prediction in the convex landscape that I'm talking about. So I'm going to consider a 2-dimensional stochastic model here. So we have these variables u and v here. As you can see, it's linear and Gaussian. Everything is linear, and I just have a Gaussian forcing here. We can think about it as the u variable as being the result dynamics, sort of the large-scale dynamics, if you like. It's a toy model. And v is the unresolved dynamics that, of course, feeds back onto the resolved one as well. It's easy in this case to derive conditions for an existence of an attractor. So the deterministic part of this dynamics, well, it will be this dot here. Of course, the full attractor is going to be, it's not a deterministic system, but the drift part of this equation is going to, I know when the fixed point is going to exist. And now I'm trying to model it by using a 1-dimensional model, again, so the baby configuration for model reduction. I have a 2-dimensional stochastic model. I'm trying to approximate now what I call the result dynamics by a 1-dimensional model, which is also stochastic. And what you can see here, well, I'm going to have 3 parameters. This is just for those who might be familiar with it. This is just a simple OU process, Ornstein-Uhlenbeck process. Well, of course, I'm losing 1 dimension here, so it becomes a bit degenerate. But what happens now? Well, the situation is kind of what I was talking about before is highlighted here. If I don't do anything, if I take a random collection of parameters in my approximate model, well, let's say the truth, the distribution of the attractor of the truth is here. My model for arbitrary parameters is going to be somewhere off. Now, by tuning the parameters, what I will attempt to do is I'm trying to get these 2 probability distributions on the attractor, the marginal ones on the variable u. I want them to agree. Well, of course, having doing only this step does not guarantee me now that if I perturb the forcing, in other ways, It's one of the ways of perturbing the attractor of the truth. It doesn't give me a guarantee that my perturbed density will stay anywhere near the truth, in principle. I argue that based on the inequality I gave you at the beginning, it does, at least gives you a way of assuring this. But let's see what might go wrong in the presence of those, depending on the features of the system. So the first thing I want to do is I want to choose these parameters. Gamma is my damping in this problem. F is just a constant forcing. I have a noise amplitude sigma m here. So I have 3 parameters, and the system is Gaussian. So what I want to do is, in this toy example, I want to tune the attractor dynamics. So what I have to do is I have to tune my mean in the result variable and my variance in the result variable. So I have 2 constraints and I have 3 parameters. Well, I'm going to be left, first of all, I can do it. Second of all, I'm going to be left with 1 free parameter. Okay, so why is it helpful? Well, because now I have this free parameter. I have a whole family of reduced models. Yes, I'm nearly done. I have a whole family of reduced models which agree with the truth on the attractor, on the resolved subspace. And I can now play with this extra gamma in order to make sure that my forced response is as good as possible. And I want to highlight one particular thing, which I will go to in the next slide. It so happens, because the model is so simple, I know what the response is going to be. I can just calculate it. If I perturb the forcing, I know what is going to be the change in the mean value of u analytically. Okay, so then again, the reason why I do this is going to become clear on the next slide. So, but I know what is going to be the change, asymptotic change of my mean of the truth, and the asymptotic change of my mean of the perturbed model, of the reduced model, if I perturb the forcing. Well, and I can then look, this is an old notation here, but this is again the loss of information between, in the perturbed density of my approximate model versus the true density when I perturb both of them. I can express it again directly here. Well, it factorizes, so well, ideally what I would like to do, if I wanted to minimize the loss of information, well, I want to minimize this part here. And it turns out that now everything depends on the sign of A. And A, notice, is a parameter which enters in the, if you like, the unresolved dynamics. So that's potentially a problem, because it will turn out that my ability to reduce or overcome those information barriers depends on something that is effectively hidden from me. Because if A is positive, well, there is no minimum. Both of these terms are positive. I can't really reduce it. Gamma is also positive. However, where A is negative, I can find an optimal value of my damping, which will satisfy both things. I will have the correct marginal density on the unperturbed attractor, and I'll also have a correct asymptotic response and an agreement on the perturbed attractor. On the other hand, in the first case, depending on what happened in my unresolved dynamics, there is not much room for maneuver there. I'm running out of time, so I'll just skip this. These slides will be, so there's various scenarios here, again, depending on the situation, if I have an information barrier versus if I don't have an information barrier. The presence of information barrier, again, if I can find an optimal gamma, that means I can reduce, in this toy example, I can reduce my model error and the perturbed dynamics to 0. In the other case, I can't do it. And then there's various scenarios here, which I'll glance over. Again, in the context of the presence of the information barrier, again, this corresponds to the situation where all my models, which I could get to agree on the unperturbed attractor, lie, if you like, on one side of this convex, on the convex landscape. And in this case, the best I can do, again, is to resort to using the single model which has the smallest, the smallest lack of information. On the other hand, as in the previous case, I could do much better. The green one was again the single model guy, by choosing various weights in the multi-model ensemble. I can actually do better than for the single best model. This was something, well, I will not go through this. This gets a bit more technical. It's related to the information bounds. I'll skip this. And maybe I'll just leave you with the summary here. Since I'm out of time, and I'll leave this in a second. The relevant publications are here, but I'll stay on the summary side. Thank you very much.
So for the IPCC AR5, there was a lot of interest in doing a model weighting, and it didn't happen for political reasons. In the U.S. National Climate Assessment, we did not have that international politics, and so there was a decision made we would do a model weighting. I contacted Ben Sanderson, and we made a lot of decisions about what would be in this. We made it centric on trying to be weighted toward North America. We did make a decision that we wanted one set of weights to rule them all, so that we could give these weights to later chapters to use. So my question is, could we use these techniques to evaluate such a model weighting scheme based on a lot of different climate model outputs to determine whether or not we actually did improve the information content?
Well,
it did make a difference in the projection, principally in precipitation. The Southwest is not as dry in the model weighted projection as it is in the unweighted.
Well, someone in the audience might correct me or criticize me. That was a sort of, ideally this would be the goal. Okay, I believe this it is possible. Whether or not it's possible, computationally possible, that is a valid point, and it might be an issue. But hopefully, I mean, the goal of it was exactly to aid this kind of a process, as you mentioned. So the answer would be yes. I believe yes. That could be. I mean, and there's various ways one, depending on how much is possible computationally, one can either decide on optimally tuning the weights, or using the second criteria, or deciding whether or not a particular set of weights was useful or not. So there's two possibilities there.
One of the challenges is that weights are based on a distance to observations or something like that. We don't yet have a set of observations or set of models. Well, I have to be brief here. We don't have metrics that predict model scatter. So I think that the models that are next to each other for modern climate diverge in future